There was a trick. The midterm's tomorrow, so I'm here tonight doing some last-minute studying. Not cramming, I'm still gonna get a good night's sleep. I mean, I need to get a good night's sleep. But I'm just here to practice some of the concepts that I feel like I haven't gotten enough practice with. And those are two in particular. Like I said yesterday, the way that I was attempting to solve the decomposition of acceleration problems was extremely complex and tedious. It was possible, but still tedious nonetheless. And it definitely wasn't something that I'm going to have time for on a test. So, I went into office hours, and lo and behold, the answer hath revealed itself to me. Well, I mean, the professor revealed the answer to me. I still think I get some credit, though. So I have made my handy-dandy note card for the test tomorrow with, I think, all the information that I'm going to feasibly need. So I think what I'm going to try and do is I'm going to try and pull up another acceleration decomposition question and do it with the information on this card. So let's get started, shall we? Also, quick apology for not having a video yesterday. I was studying for this calculus exam with a friend, and I didn't have time to make a video. But we're getting one done tonight. Rain, sleet, snow or shine. That's right, we're the US Postal Service. So, say we're given a position vector and we want to find the unit tangent vector and the unit normal vector. Now, the way we were doing this before, it got tricky around the normal vector. The derivative of the unit tangent vector was a little hard to find, at least by hand. If we have access to Wolfram Alpha on any of our exams, I guess it won't be a problem whatsoever. We needed a good and easy and simple and understandable way to find the normal vector. And we have exactly that. If we simplify the acceleration equation down, we see that it is equal to the acceleration in the tangent direction times the unit tangent vector plus the acceleration in the normal direction times the unit normal vector. So this is going to be equal to v prime tangent naught plus kappa v squared normal naught. We find the first derivative, and then we use our trig identity to simplify it down and make it a little bit easier for us, and then we find the second derivative. Now keep in mind that this second derivative is, in fact, equal to the entire acceleration vector, and that'll be important. So now we found the value of velocity, which is just the magnitude of the first derivative of the position vector. Damn it, I messed up the trig identities. I'm just going to put a square on this one to make it a little bit more clear. I've moved all of our equations that we have up there. An important thing to realize about doing these problems is it's really about compiling all the necessary ingredients to put together into the formula. It's like we're making a calculus soup of parametric equations. Not very delicious, but highly useful. Like castor oil. Does castor oil actually have any medicinal benefits? I think I'm getting distracted. I mean, I guess there are a lot of substances that are highly effective, but not very delicious. Crude oil, napalm, cyanide? Does cyanide have any uses? Right, calculus. The next thing that we are going to be calculating is T naught, the unit tangent vector. And as we know from last night, the unit tangent vector is going to be equal to r prime divided by the magnitude of r prime, or r prime divided by velocity. And looky here, we have both those things. What a coincidence. This puppy is going to be equal to our unit tangent vector. Now, if we were to find the unit normal vector using derivatives, we would need to differentiate this. That sounds disgusting. I feel myself getting sick at the very idea. I mean, even if we make this equal to the quantity raised to the -1/2 power, that's still chain rule, multiple product rules. It's gross. We don't want to do that. But luckily, we don't have to. Let's keep going. So now we've brought back our equation. Now the tangent component of the acceleration is going to be given by v prime. which, as it turns out, is equal to r prime dot r double prime over the magnitude of r prime. Now, the acceleration in the normal direction is going to be given by the magnitude of the cross product of r prime cross r double prime over the magnitude of r prime. Notice how both of these values in the denominator can be written as v, because v is, of course, the magnitude of r prime. This is something that we can solve for. This may seem like it's going off in random directions, but I promise you it will all come together. What we are basically trying to do is we are trying to find all the components of this equation up here except the normal unit vector. Because as soon as we find all the other components, we can solve for the unit normal vector. First, let's solve for the dot product of r prime of t and r double prime of t. So if we add up the products of all the components, we get that the dot product of r prime of t and r double prime of t is 8 sine t cosine 2t. Did that have beat to it? Hold the phone, y'all. I think we can simplify this further. Oh my god, you can go even further. Does that work? That can't work. Give me a minute. Yeah, this isn't true. This is where we're gonna have to stop. So finally, we can use our dot product to find the acceleration in the tangential direction by dividing it by the velocity. Cool. Let's use that same strategy to find the acceleration in the normal direction now. Except there's going to be one more step. We are going to need to take the magnitude of the cross product after we find it. So let's go. Let's see how this turns out. That seems way too clean. I am automatically suspicious. But I also do not have time to check my work. Let's roll with it. They better give us a lot of scratch paper for this. Also, I'm going to need to make sure that I actually read the question. If they just ask for acceleration at a certain point, all I need to do is find the second derivative and plug in the point that they give me. If they don't ask me to decompose the damn thing, I'm not going to. Oh. So this is the magnitude of the acceleration in the normal direction. If we multiply this times the unit normal vector, we are going to get a vector that points in the acceleration in the normal direction. Cool. So now we have everything that we need to solve for the unit normal vector. Let's see if I can get this done in the next 10 minutes so I have time to go over the next topic. So now recalling our equation. To start unraveling this thing, we subtract this from a, which is r double prime of t. And that is going to leave us with a sub n times the normal unit vector. I don't think this is easier than taking the derivative of the unit tangent vector. Now that I'm thinking about it, there was a place in this strategy where I was supposed to plug in a value for t into some equation, but I don't know where and I don't know when. I'm frustrated because right now I'm going in on the hope that this is not on the midterm tomorrow. But I know that in all likelihood it is, because midterms for me have an uncanny ability to produce the material that I always feel least confident about. Probably just a placebo though. From here you would multiply each of these components by the reciprocal of the acceleration of the magnitude of the acceleration in the normal direction. That I don't think that would make this any cleaner. I'm at a bit of a loss right now. Well, that's disappointing, but I think I need to get to bed. I mean, I could hit my head against this brick wall for the next hour and a half, and I'm not sure that I would make any more useful progress. I mean, the coherent strategy to solve this isn't covered in the textbook or in the notes. I'd probably have to scour YouTube for half an hour to find a solution to this. Well, that's a high note to end on going into the midterm. I'm nervous, but I can do this. And I will not accept anything less than my full effort. I'm going to make a pact with myself right now that I'm not going to leave the testing space until the entire time is up. If I finish early, I'm going to spend the entire time checking my answers. I'm going to get the highest score on this test that I possibly can. Because if I don't, What will all this hard work be for? I think that's gonna call it for the night, y'all. Thank you so much for watching me do things. Are you a masochist too?